Hey guys, you might be wondering who this is. Hopefully that will give you a hint. It's F Train. You know me, right? Anyway, I am just excited to do another lesson with you guys. And we're going to be talking today about pulsars. And we're going to bring it home to Bronx Science today, just give you a little advanced notice there, right? Hopefully you're all doing fantastic. Let me take a sip of tea. And please don't call me Mr. T, okay? I'm F Train. All right, so let's start out with our do now today. Do now is why do neutron stars spin so fast, right? So you might want to pause and think about that for a minute. Why do they spin so fast? Okay, hopefully now you thought about it and you realize that the reason they spin so fast is that you had this huge iron core and it might have been spinning really slowly, might have had a little bit of angular momentum. But then when it collapses and it becomes like the size of Manhattan, angular momentum is conserved. So now that the moment of inertia has decreased greatly, like by a factor of thousands, the rate of spin will also increase by that much in order to conserve angular momentum. And that's why neutron stars spin so fast. And hold on to that because that's going to become important in today's lesson. Okay. All right. So this young lady her name was Jocelyn Bell. I think she's still around. I think she's just not a young lady anymore. Anyway, this is back in the 60s. She was at Cambridge University and she was looking at data from a radio telescope. And she saw this strange pattern of kind of blips on the data. And so anyway, if you look at that, think about it. What question does this raise? And the question that it raises is, what caused the strange pattern on the radio telescope data? So this is intensity versus time. And so you get these little blips of high intensity. And you can see they're separated by a certain amount of time, and they look like they're pretty regular in time in terms of their period. Okay. So, so of course, when they saw this, there was, a little bit of excitement because you don't generally see patterns like this. So some of the first, probably like the first obvious thing is there something wrong with the equipment? Is it picking up like a radio station that's not, it's not registered, or like a pirate radio station or something like that? Okay. Then of course, the logical thing was, is it intelligent life? Is intelligent life trying to contact with us? And that got people pretty excited. And in fact, these blips on the screen were originally called LGM. And you can pause for a second and think about what LGM might stand for. Yes, little green men, because of course people always thought that the man from Mars, was the sort of the prototype alien, was green or something. Okay. Anyway, but eventually similar signals were found in other parts of the sky, and they were pulsating with different frequencies. So it was concluded that it must be natural. And so the name LGM was dropped for the name pulsar. And you can think about what pulsar might be, kind of a shortened form of, it's a pulsating star. And by the way, my producer tells me that when you blend two names together like that, it's called a portmanteau. I think it's French. Anyway, So what is a pulsar? Basically, pulsars emit radio frequencies every 0.033 seconds to 3.75 seconds. I guess that's the range that we have discovered, at least up until now. The pulses last around 1 millisecond, and they are to atomic clock precision. In other words, you can literally set an atomic clock by the regularity of the pulses of a pulsar. They're fairly rare. There's only about 2,000 known. However, it's thought, based on what we'll learn today, that there might be up to like, what is that, 100 million in our galaxy alone. So, you know, they're rare in the sense that we've only discovered 2,000, but there may be many, many more than that. They emit electromagnetic radiation over a large range of frequencies. There are some pulsars emitting radio frequencies, visible, X-ray, etc. Okay, now we learned about another type of star that varies its brightness. Okay, you might remember variable stars. And how do variable stars change their brightness? So why don't you pause and try to recall, maybe write a note in your notebook about how do variable stars change their brightness. Let you pause. Okay, and you might remember the pressure, temperature, thermostat, etc. You know, as the star expands, it gets brighter, and then it contracts, it gets dimmer. Okay. Now, could this explain a pulsar, or might a pulsar just be a star that has like a hot spot on it, and as it turns, as the star spins, that hot spot, you know, faces us, and maybe you know, that's when it gets bright, those little blips of brightness. And if so, what kind of star might this be? Now, there's a law in physics that says, and oh, and by the way, would it fly apart if it was spinning that fast? I mean, think about a star that was spinning even at its slowest every 3.75 seconds. You know, the sun turns every like once a month, you know, so think about a star that would be turning once every few seconds. You know, chances are the forces would just blow it apart. There's a known principle in physics that says an object cannot change its brightness in an interval shorter than the time it takes light to cross its diameter. Okay, so if the brightness is changing in an interval of 0.001 seconds, that means that a pulsar needs to be less than 300 kilometers in diameter. Now, there's another hint that sort of helped them figure out what pulsars were, and that is that there is a pulsar found in the middle of the Crab Nebula. Now, you might remember the Crab Nebula in our previous lesson when we talked about supernovae. So, what conclusion? Well, I'd like you to pause for a second and, you know, think about that for a minute. What conclusion might be drawn about these facts? And the conclusion is that a pulsar is a neutron star. Okay, pulsars are basically neutron stars. Now, the question is, though, how do pulsars pulse? How would a neutron star pulse light? Okay, and the most common explanation of this is known as the lighthouse theory. And basically, pulsars don't actually pulse, but they emit beams of radiation sort of out the tops and bottoms. So you have these, and it has to do with magnetic fields. It has to do with, you know, particles being, you know, energized by magnetic fields, etc. but you have these beams of radiation that are going out the top and the bottom. And as this pulsar is spinning really fast, this sort of beam is going to be, kind of spinning around, almost like the beam of light in a lighthouse. That's why they call it the lighthouse theory. And if you've ever seen a lighthouse at night, you have this beam of light that sort of turns around, and then, as it passes a ship or whatever, the ship then can see that beam of light. Okay. Now, the mechanisms that produce the beams are not fully understood. Like I said, though, it has to do with magnetic fields. Now, how would this produce a pulse? Well, sort of as we alluded to, you could imagine that this beam is rotating, and so when the pulse crosses the path of the Earth, it would be seen. So why aren't pulsars detected in all supernova remnants? Well, first of all, not all super remnants include neutron stars. Okay, now you might recall that as when we talked about supernovae, we said that if a star is less than 3 solar masses, between I think 1.4 and 3 solar masses, if the iron core was that big, it will produce a neutron star. If it's greater than that, you will probably recall that it would actually form a black hole. So not all supernova remnants include neutron stars. Secondly, as we just mentioned, pulsars are only visible if the beam hits the Earth. Now, space is a big place, and this beam, if it's whirling around, I mean, think about, there's only really a plane that this beam is going to be, revolving around in. And if that plane does not intersect the Earth, then, we're not going to see it. Okay. And then there's another thing at asymmetric supernovae. Sometimes when if you can imagine when hold on a second. So like if you have your iron core here in the center, and this is sort of the gas that's on the outside, if it explodes sort of evenly, it'll just blow everything outward. But if it explodes asymmetrically, you might have a situation where the iron core or the neutron star is going to blow out sort of to the right a little bit, which means if momentum is conserved, then the rest of it is going to get kind of blown out in that direction. And this, so basically you could have the neutron star and the planetary nebula sort of moving away from each other. And so that might also be a reason why you don't have a neutron star in the middle of all supernova remnants. Russell Hulse, you may have seen his picture if you've ever walked through the halls of Bronx Science, especially in the lobby there. And one day, this graduate student, when he was a graduate student, was observing pulsar data, and he noticed that the period of the pulsar was actually changing. It was increasing and decreasing. Why might this be happening? And what you might want to do is think back to our discussion of the Doppler effect. Okay, and we talked about how that when you have binary stars, you'll have one star spinning around the other one, and the stars, as they are moving toward away from us, it shifts the spectral lines of those stars, and so the period here might be changing due to the Doppler effect. Also, where did Russell Hulse go to high school? Well, he went to Bronx Science. Anyway, so what did Russell Hulse discover? Well, he discovered something called a binary pulsar. And basically, two neutron stars separated by a distance equal to approximately the radius of our sun. So this is a very, very small distance. Okay, and due to the Doppler effect, the period increases and decreases. So in 1993, Russell Hulse, along with his advisor, professor, I guess, Joseph Taylor. Now, I believe they did this the discovery was made back like in the 70s, but um, the way the Nobel Prize works is it takes a while for them to kind of confirm the discovery, and all the papers are written, and everybody is on board and people have to vote. It's kind of like getting, maybe similar to making it into the Hall of Fame. You don't always make it on the first ballot, etc. But anyway, sometime later he was awarded the Nobel Prize. And the really cool thing, one of the things I really like about this story is that Joseph H. Taylor Jr. Didn't really need to kind of share this Nobel Prize with Russell Hulse. In other words, when this discovery was made, I mean, Hulse was working for Taylor. And so, Taylor could have just said, thank you, great discovery, but I'm the professor. And so, I get my name on all the papers that are written, and it would have been seen as his discovery because Hulse was basically just working for him. It's kind of like if you go to a restaurant and you look at the menu, it'll say, chef, Louis, whatever. Well, chances are Louis, whatever, did not actually cook your meal, but he gets credit for cooking your meal because he's the one who, kind of designed, you know, designed your meal, if you will, or, planned the recipe, maybe wrote the recipe, etc. So similarly, in things like this, a lot of times the professor will get the credit for something that maybe one of their grad students had actually found or discovered. So this guy was a pretty good guy to sort of share the glory, and so they joint received this Nobel Prize. Okay, so in summary, explain to your neighbor how pulsars pulse. Notice I have a video here. I'm not going to show the video on this video, but I'm going to link that video in the notes or in the Google Classroom document, and you can watch that if you want. Anyway, hope you guys have a great day, and I will talk to you very soon.